Conventional takeoff and landing, a tried and true way of getting aircraft off the ground and into the sky, demanding long runways so that the aircraft can build up enough speed so that the airflow over its wings can create sufficient aerodynamic lift for takeoff. Effective, but with limitations on where it can operate. The helicopter, a rotorcraft capable of taking off and landing vertically where an airplane never could, but without the range, speed, and payload capabilities of a conventional airplane. A way to combine the best of both would seemingly be the ideal, and to this end, NASA's Ames Research Center in Mountain View, California, has been devoted since 1951. What has arisen from this effort is a new technology called powered lift. Powered lift aircraft incorporate new rotors or jet propulsion systems that allow the aircraft to take off and land in very short distances, even vertically, and hover while maintaining the range, speed, and payload capabilities of conventional aircraft. A new era in aircraft design has been emerging, which improves on theories of aerodynamic lift. What you are about to see are several powered lift aircraft and concepts, a look into the near future. The Tilt Rotor is an advanced rotorcraft that is the realization of many years of work and talent. Its success hasn't been overnight. Today, the XV-15, the second generation in the Tilt Rotor lineage, is being test flown at NASA Ames and has even made public appearances. The XV-15 is an aircraft that can take off, land, and hover like the helicopter, yet carry the payload and achieve the speed and range of a turboprop airplane. It is the rotation of the engine pods from a vertical to a horizontal position that transfers the lift from the propellers to the wings and lifts the tilt rotor into aviation history. The tilt rotor design is a vast improvement over helicopter technology. During cruise, the helicopter's main rotor spends most of its energy providing lift rather than providing forward motion for the aircraft. The tilt rotor doesn't have this problem. Once aloft, its thrust can be used for speed. It can hover nose up or nose down. It can fly forward or rearward or sideward. It rides smoothly and quietly and is both fast and fuel efficient, making it an ideal alternative to commuter airplanes, especially in heavily congested urban areas. The tilt rotor can quietly land in heliports to help alleviate airport runway congestion, the leading cause of airplane delays, without disturbing local residents. As a rescue aircraft, the tilt rotor has twice the speed of the helicopter and can deliver more supplies in a shorter time over a larger range. The XV-15 tilt rotor carries a crew of 2 and has a cruising speed of about 300 knots, more than twice as fast as commercial helicopters, and carries a fuel load that allows it about 1 hour of flight. The XV-15 has been so successful as a proof-of-concept test vehicle that the next generation tilt rotor, the Bell-Boeing V-22 Osprey, has been designed. The Osprey is scheduled to make its first flight in June 1988. Designed to replace the existing medium-lift helicopters flown by the U.S. military, the U.S. government will buy over 900 V-22 Osprey tilt rotors. Plans for a commercial version of the Osprey will feature all the comforts of conventional commuter aircraft and carry 44 passengers. The Osprey will fly non-stop for 800 miles and will be a common sight in the skies of large cities as it hovers and lands in downtown heliports across the country. As exciting as the tilt rotor is, there are now plans for other advanced rotorcraft. One of the greatest technical challenges in recent aeronautics research is the creation of an advanced rotorcraft called several unique research aircraft with short takeoff and landing capabilities have been tested and perfected. The Augmentor wing aircraft was the world's first jet short takeoff and landing, or STOL, transport aircraft. Tested and developed by NASA Ames and the Canadian government, the Augmentor wing demonstrated a concept of increased or augmented lift capabilities for a STOL aircraft. In the Augmentor wing aircraft, additional cold airflow was entrained by the hot exhaust in order to provide increased wing lift as compared to a conventional aircraft. Taking the idea of improving STOL capabilities one step further, the quiet short-haul research aircraft was developed. This low-speed research vehicle has been an important source of valuable data on powered lift aircraft performance in the low-speed regime. The QSRA uses a unique propulsive lift technique called upper surface blowing in a 4-engine configuration. Upper surface blowing works by blowing the jet engine exhaust over the top surface of the wing. Airflow tends to follow the curve of the wing. Flaps are added to the wing of the QSRA to encourage the airflow to continue on a downward curve. These flaps are extended during approach and landing to provide greatly increased lift. Upper surface blowing propulsive lift enables the wing to generate 3 times the lift of a conventional wing at low speeds. This increased lift allows for slower and safer arrivals and departures, but in a fraction of the runway distance needed by conventional jet transports while carrying a heavier payload than a comparable aircraft of its size. STOL capabilities will be extremely valuable aboard aircraft carriers where runway space and aircraft arresting gear is severely limited. The acoustic advantages of the QSRA are also attributed to upper surface blowing. Because this technique requires the engines to be mounted directly over the wing for airflow purposes, much of the noise of takeoff and landing is deflected upward and away from communities that neighbor airports. In commercial use, QSRA's quietness and maneuverability allow it to approach airports from alternate paths, which may someday significantly help alleviate airport congestion. Currently, the Japanese ASCA, a STOL design which uses upper surface blowing, is being prepared for flight test. Although the QSRA is a proof-of-concept research vehicle, its ability to quietly take off and land on short runways, and its ability to carry 25% more payload than conventional aircraft make it an exciting and promising research investment, one that may lead to a new generation of short takeoff and landing aircraft. A high-performance breed of powered lift aircraft that has the capability for both vertical and short takeoff and landing has emerged for accessing areas without full-length runways. Known as VTOL aircraft, these designs can operate despite damaged runways and can land on ships at sea that are not equipped with elaborate catapult and arresting gear, equipment necessary to safely launch and land today's jet fighters. NASA, Grumman Aerospace Corporation, and the U.S. Navy are jointly investigating a subsonic VTOL jet called the Tilt Nacelle. As its name implies, the Tilt Nacelle utilizes engine pods which can tilt at angles to achieve vertical lift or forward propulsion. The Tilt Nacelle features movable vanes which channel the engine exhaust to provide control of the vehicle in hover flight. Although still in the research phase, a full-scale model of the Tilt Nacelle in NASA Ames wind tunnel shows that the aircraft could be very efficient, safe, and controllable throughout all phases of flight. Testing in flight simulators at Ames has shown that the Tilt Nacelle would be easy and safe to fly. First tested on a piloted simulator at NASA Ames, the Harrier is currently the only powered lift fighter airplane that is operational in the free world. The Harrier can take off and land vertically. In the normal STOL mode, it can take off in less than 400 feet and in less than 1,000 feet in an overloaded condition. The Harrier can fly at high subsonic speeds and operate at sites that are impossible for conventional aircraft. The Harrier accomplishes this by vectoring the thrust from its turbofan engines to provide the vertical lift. Its vectored thrust engines enabled the Harrier to prove itself repeatedly in all phases of testing and in actual combat. Operational use of the Harrier has shown that it is most often operated as a short takeoff and vertical landing, or STOL aircraft. Short takeoff maximizes the payload of weapons and fuel that the Harrier can take into combat. The Harrier has been so successful that it is now a mainstay of the U.S. Marine Corps and will play an increasingly active role in airborne military capabilities in the free world. The effectiveness of STOL operation has led to research into the technology for future supersonic STOL fighter aircraft. This is an artist rendering of the proposed Lockheed hybrid fan-vectored thrust supersonic STOL concept. The HFVT is a shoulder-wing, single-turbofan engine aircraft design. The engine is centrally placed in the fuselage with two nozzles, also centrally located, one under each wing, and a third nozzle at the end of the fuselage. This nozzle receives only hot exhaust from the engine core, known as core air, and vectors it downward for vertical takeoff and landing. The nozzles located under the wings vector cooler flow air or bypass air that has not passed over the engine core downward, helping to balance the aircraft and creating additional lift during takeoff and landing. Once airborne, the core air and bypass air are mixed and vectored straight back for high-speed cruise. During cruise, the side nozzles are vectored aft and are not active. During low-speed cruise, bypass air is diverted through the side nozzles for improved efficiency. The nozzle at the back of the fuselage can be vectored anywhere between the lift or cruise positions to accomplish speed control and hover. This is the proposed McDonnell Douglas 279-3. The propulsion system intended for this aircraft is the plenum chamber burning vectored thrust concept. This is a single-engine, four-nozzle configuration with two nozzles positioned in the center of the aircraft on either side of the fuselage and the other two farther back on the aircraft behind the forward nozzles. In the PCB thrust mode of operation, bypass air is mixed with fuel and burned in the forward nozzles where it is heated for increased thrust during vertical takeoff and landing. These nozzles are vectored back during high-speed cruise. The nozzles toward the back of the airplane receive core air and are also vectored downward for vertical takeoff and landing and straight back for high-speed cruise. Unlike the hybrid fan-vectored thrust, the PCB vectored thrust never combines bypass air with core air. All four nozzles are continuously vectorable for speed and hover control. This is a drawing of the General Dynamics E-7 supersonic fighter concept, which utilizes an Augmentor ejector propulsion system. The E-7 uses a single-engine, dual-nozzle, and dual-ejector Augmentor configuration. Ejector augmentors entrain secondary air over the top of the fuselage to create additional lift. On the E-7, the two ejector augmentors are located one in each wing, close to where the wings join the fuselage. The core air nozzle is toward the rear of the fuselage, and the fan air nozzle is augmented in the ejector with outside air. This nozzle is vectored downward for vertical lift during takeoff and landing. During high-speed cruise, core air and bypass air are combined, then vectored straight out the back of the aircraft. For hover and speed control, this nozzle can be vectored at varying degrees. The Augmentor ejectors receive bypass air through a ducting system from the engine. Additional thrust is obtained by entraining ambient air, which mixes with the higher pressure bypass air. This air is then directed downward to increase vertical lift and provide balance forces during takeoff and landing. During high-speed cruise, the ejector augmentors are not active and are folded up out of the way. The remote augmented lift system concept is a propulsion system being considered for a Grumman design. The Grumman Rawls has a canard wing configuration and is equipped with two engines and four nozzles. The engines are positioned side by side in the center of the fuselage. Each engine has a forward and a rear nozzle. The two forward remote nozzles sit side by side behind the pilot. The main nozzles are located farther back on the fuselage behind the engines. The remote nozzles receive bypass air from the engines via a ducting system. A duct burner inside the nozzles heats the air before it is vectored downward for lift and control during takeoff and hover. These nozzles are inoperable during high-speed cruise. The nozzles in the back of the Rawls receive only core air during vertical takeoff and landing and are vectored down. During high-speed cruise, these nozzles are vectored straight back and the core air is combined with bypass air to provide further thrust. These nozzles are vectorable during aircraft operations and assist with the airplane's maneuverability, low-speed cruise, and hover capabilities. The last supersonic STOL concept of tomorrow is called the Lift Plus Lift Cruise. The name reflects its design. One engine is installed with the sole purpose of achieving vertical lift, the other for producing lift and cruise thrust. These propulsion systems and proposed jet fighters are the shape of tomorrow. The many advantages of combining the sleek form of supersonic aircraft with powered lift capabilities make it well worth the challenges. A fast, highly maneuverable aircraft that can take off and land where current supersonic jet fighters never could will be the ultimate. Powered lift technology today has already taken to the skies in the shape of the Tilt Rotor, the QSRA, and the Harrier. Tomorrow, powered lift technology will play an ever-increasing role in air transportation, rescue, and military missions, and in opening frontiers that until now were inaccessible to aircraft. The time for something new has definitely arrived.